A number of testing principles have been suggested over the past 40 years and offer general guidelines common for all testing. Testing shows the presence of bugs. Exhaustive testing is impossible. Early testing. Defect clustering. Space-side paradox. Testing is context dependent. Absence of errors falsy. Principle number 1. Testing shows the presence of bugs. When you test a software, you may or may not find defects. If you find defects, then that's a proof of the presence of bugs. But on the other hand, if your test didn't find defects, that's not a proof that the software is error-free. There's a great probability that you didn't find defects because your test doesn't cover the breadth and width of the software. Maybe you didn't select the right test data to exercise the software. Maybe the defect is waiting for a very special circumstance to fail the software. Remember the Y2K problem, where many software solutions failed because they only consider the year as a 2 digits only, assuming it will always add to 1900? If you think about those software solutions, they used to work perfectly in the 70s, 80s, and 90s, but they couldn't operate starting the 1st of January 2000. Therefore, those solutions contained defects that were waiting for a special date to show on. So we can't call those solutions to be bug-free, even though they were working perfectly for ages. So there is nothing called bug-free software. There is no way we can prove that. We simply need to design as many tests as possible to find as many defects as possible. Principle number 2. Exhaustive testing is impossible. Imagine if we have a web page from where you need to enter the age of the employee, which should be in the range 20 to 50. To test this field thoroughly, you need to enter all the possible values in that field, the valid and invalid ones. So if this field accepts an integer, which ranges from minus 32,767 to 32,767, then we have 65,535 possible values. Add to it a bunch of combinations of text values and special characters. Well, the user might type text by mistake and you want your software to behave decently in all cases without crashing. Also, we might need to test special test cases where we paste numbers, not typing them, drag and drop the values, and maybe try some special circumstances when entering the values like putting spaces, delete characters, and so on. Then say we have a total of 70,000 values. If each value needs 1 minute to be tested, and that's very short by the way, then we would need 70,000 minutes to test this field alone. 70,000 minutes is 1,167 hours, which is 49 days testing a single field day and night. Unless the application under test has an extremely simple, it's not possible to test all possible combinations of data input and circumstances. We call it preconditions. Testing all possible data combinations is called exhaustive testing. Hence, exhaustive testing is impossible. For this reason, risk and priorities are used to concentrate on the most important aspects to test. Their use is important to ensure that the most important parts are tested. Principle number 3. Early testing. Many problems in software systems can be tracked back to missing or incorrect requirements. In early testing, we are trying to find errors and defects before they are passed to the next stage of the development process. From the shown graph, when a bug in the requirement is discovered during the requirement phase, the cost of fixing this bug is very cheap. The more we wait on fixing this bug, the more costly it is to be fixed. Why? Because now we might have built some of our design based on this faulty requirement. Same thing when a bug is introduced in the design phase. It's cheaper to fix it in the design phase than wait until further stages, and so on. A bug in the requirement would create the wrong design, which in turn would create a buggy code, and the final result would be a buggy software. From the shown graph, we see that if a customer discovered the bug after delivering the software, it would cost as 1,000 times higher what we would pay if we discovered and fixed the bug in the requirement phase. In addition, the time and effort required to fix a requirement bug during the system testing phase could be 500 times higher than if we would have discovered and fixed the bug in the requirement phase. What we are trying to achieve here is to break the error defect failure cycle we mentioned earlier. We can do that by trying to find defects early. Testing activities shall be started as early as possible in the software or system development lifecycle. Testers should join the software lifecycle as soon as the documents are in draft mode. For example, are individual requirements testable? Can we find ambiguous or missing requirement? If we wait until the last minute to introduce the testers, time pressure can increase dramatically. Therefore, there is a real danger that testing will be squeezed. The earlier the testing activity started, the longer the elapsed time available. Testers do not have to wait until software is available to test. Principle number 4. Defect clustering. If we have a software of 10 modules or components, imagine that our third cycle of testing exposed 100 bugs. You won't find that each module has exactly 10 bugs, but rather it's often a small number of modules that exhibit the majority of the problems. This can happen for a variety of reasons, some of which are the system is very complex in this module, volatile code, the effects of a change upon a change on this module, or development staff inexperience. This phenomenon is closely related to the Pareto principle, which is called the 80-20 rule. It says that approximately 80% of the problems are found in about 20% of the modules. So if you want to uncover a higher number of defects, it's useful to employ this principle and target areas of the applications under test where a high proportion of defects can be found. However, it must be remembered that testing should not concentrate exclusively on those parts. There may be fewer defects in the remaining code, but testers still need to search for them. Principle number 5. Specified paradox. If the same tests are repeated over and over again, eventually the same set of test cases will no longer find any new defects. To overcome this pesticide paradox and to find new defects, test cases need to be regularly reviewed and revised. And new and different tests need to be written to exercise different parts of the software or system to find potentially more defects. Principle number 6. Testing is context dependent. Different testing is necessary in different circumstances. A game software that uses graphics heavily will be tested differently than a medical software that also uses graphics heavily. A simple static website will be tested differently than a dynamic e-commerce site, where goods can be bought using credit and debit cards. A software used in an airplane will be tested differently than a flight simulator. Risk can be a large factor in determining the type of testing that is needed. The higher the possibility of loss, the more we need to invest in testing the software before it's implemented. Last principle, principle number 7, absence of errors fallacy. Software with no known errors is not necessarily ready to be shipped. Does the application under test fulfill the user's needs of it? The fact that no defects are outstanding is not a good reason to ship the software. Before dynamic testing has begun, there are no defects reported against the software. Does this mean that software that has not been tested at all can be shipped? I don't think so. Okay, now to the good part of this lecture. What kind of questions you can get in the exam regarding this lecture? Well, for one, they can list 4 options. 3 of them are principles and the 4th is not a principle, and they ask you to pick the non-principle amongst. Of course, they will make the non-principle one a confusing one. Something like, testing helps gain confidence in the software. Well, it's a true sentence, but it's not a principle. In addition, they can give you a situation and ask you which principle did the situation describe or which principle the situation is lacking. For example, a customer gets the software but he is upset because the software doesn't meet his needs. Which principle are we talking about? Absence of errors fallacy. A team wants to discover as many defects as possible. Which principle should we follow? Defect clustering, and so on. Now, if testing shows only the presence of defects and exhaustive testing is impossible, plus the best side paradox, a good question could arise now. How much testing is enough? The answer is, it depends on the risk. The risk of missing important faults. The risk of failure cost. The risk of releasing untested or under-tested software. The risk of losing credibility and market share. The risk of missing a market window. The risk of over-testing, ineffective testing. Every time we should evaluate the risk of the current situation of the software and decide whether the risk is high or low. If the risk is low and acceptable, then we can stop testing and ship the software. Otherwise, we should continue testing. Testing should provide sufficient information to stakeholders to make informed decisions about the release of the software being tested for the next development step or handover to customer. Then we use this risk information to determine what to test first, what to test most, how thoroughly to test each item, what not to test, allocate the time available for testing by prioritizing tests. We will talk more about risk and testing in a later section. Thank you.